So what we're going to talk about is we're going to talk about MPI plus OpenMP. So we'll do that for the whole morning. There's quite a lot to it, and there's an exercise there. It's one slide deck, and I'll carry on. So basically, this whole day is about how to exploit the fact, take advantage of the fact that modern supercomputers are not single core nodes, but each node is a shared memory multiprocessor, just like your laptop. And the default MPI model just ignores that. You know, you run n processes on n CPU cores, and you don't really take advantage of the fact that some of those processes are on the same physical node, and some are on different nodes. Now you can see that by doing a ping pong. You could tell if they're on the same node by doing this MPI get processor name or by doing a ping pong, but there's no way of explicitly taking advantage of it. And it might seem crazy in MPI or in parallel programming in general that you have two processes on the same physical machine. They can, in principle, share memory. You know, they're attached to the same physical block of memory, and yet to communicate with each other, they send and receive messages. That might seem a bit bonkers. So I'm going to cover two ways of taking advantage of the fact that processes are on the same physical node. One is MPI plus OpenMP, and the other is the MPI RMA model, which is native to MPI. So I will get up the OpenMP slides. Okay. So there we go. So I'll lecture for about 40 minutes, 45 minutes. Then we'll have a practical, and then I'll carry on after the coffee break. So I'm going to talk about motivation as to why you might want to do this. Then I'll talk about potential advantages and potential problems. So most of this talk will be actually trying to dissuade you from jumping into this, because it is not a magic bullet, a silver bullet. It may not work, and it does potentially incur quite a lot of programming overhead. And so I've seen people make the mistake in the past of decide they're going to do a hybrid MPI OpenMP, go away, do a lot of stuff, write the code, come back, and the code doesn't go any faster. So if there's one thing I would say is, before you embark on this style of programming, you should really convince yourself that you think that it's good, that there are good reasons why it will be worthwhile. So I'll talk about the motivation, the potential advantages of it, problems with MPI, and then I'll talk about the various styles. There are various styles of MPI and OpenMP programming. I'll basically cover the most basic style in the first lecture, and then we'll carry on to the more advanced usage in the next lecture. So as I said, I've mentioned this just in my preamble. Almost all current CPU systems are clustered architectures. So there are distributed memory systems where each node consists of a shared memory multiprocessor. And for example, on ARCHER2, we have about 6,000 nodes. Each node has got 128 CPU cores in it, all connected to the same block of 256 gigabytes of memory. Your laptop might have, I don't know, 4 CPU cores connected to whatever, your 64 gig of memory or whatever you have. So the important point is there's a single address space within each node. What that means is that in principle, processors, tasks running on your computer can read and write to the same memory. Of course, separate nodes have separate address spaces. Separate nodes are different computers. So my computer here can't write to the memory of Josh's computer, for example. They're under the control of different operating systems. But within a node, now the problem we have is that modern operating systems are specifically designed to make it difficult for processes to interact with each other. That's deliberate. You know, if you're running, if you write a program which has some bug, and you declare an array, and it runs, and your program, which when you run it becomes an operating system process, if you run off the end of an array, it would be a disaster if that carried on writing through memory and then wrote over another piece of memory which was being run by. It might corrupt a Word document or a browser or running. So processes, the way modern computers work, processes are incredibly shrink wrapped from each other. They, in fact, they really are not allowed to look outside of their domain, and that's to make your computer safe and make sure that programs don't corrupt each other. However, what we want to do here is we actually want programs to talk to each other by reading and writing to the same memory, and there are a number of ways of doing that. But the obvious way is something called OpenMP. Now, if you've done OpenMP, what you do is, we run courses on this, but what you do is you write a single so the important point, when you run a parallel program in MPI, say I wanted to use up all the CPU cores on an ARCHER2 node, I would launch 128 processes, and each process would run on a separate CPU core, but they would be very ring fenced from each other, and it would be difficult. We'll see a mechanism in the afternoon for doing it, but by default it's very difficult for them to share memory. So that they can send messages to each other, but they can't read and write to the same memory. In OpenMP, what you do, if I wanted to use all 128 CPU cores on an ARCHER2 node without OpenMP, what I do is I write a single program. I run one process. So initially it's just running on one core, but at runtime, that process spawns multiple threads, and threads are the difference between a thread and a process in Linux is really quite marginal, but they're fundamentally different in that threads are designed to be able to share memory. So if you allocated an array in the process and then you spawn multiple threads, they're like mini programs, they can all read and write to these shared arrays. So you have a single process with its ring-fenced memory, but the process is parallel. It runs multiple threads, and those threads can then can share memory. So that's the important point. So how could we program such a system? Well, we could use MPI across the whole system. Now I've got 8 nodes. I could run 1,024 MPI processes with 128 on each node. You cannot use OpenMP threads across a whole system. The way it works, as I said, is the threads are spawned at runtime by the operating system. All the threads have to be in the control of the same operating system. So basically, a process or a thread cannot migrate outside of my laptop to another laptop. So once you've launched a process or launched threads from that process, they are bound to the node that they started on. You can fake it up in software, but it doesn't really work. So, however, how about using OpenMP threads within a node and MPI between nodes? We have 8 nodes. Let's run 8 MPI processes, say, and have each MPI process spawn 128 threads. That would use up all our CPU cores, but is that a useful thing to do? So the reason why MPI plus OpenMP programming is difficult is actually because the MPI developers, MPI programs are surprisingly efficient. You might think that it's a bit weird to have 128 MPI processes on the same node, all sending and receiving messages to each other when they could just, in principle, read and write to the same memory. However, as we saw yesterday, MPI developers are very good at taking advantage of this. So if you send messages between 2 processes on the same node, you don't have the huge overhead of it doesn't go out the network and back again. There are lots of shortcuts put in. So actually, if you do this at the small scale, then you won't get any benefits. However, what we tend to see is that the benefits come with MPI scalability. Now, time or memory, I'll mention them both, runs out. So MPI plus Open. So if you come to me and say, like, I've got this MPI program, it runs very efficiently on small core counts. By the time I get up to 5,000 or 6,000, it just stops scaling. Then you might think, well, maybe MPI plus OpenMP would help you there. However, it is a challenge because you're looking for performance improvements at the very high end, but of course you develop your software on a few nodes at the same time, so that can be challenging. But the scalability can be in terms of both memory or time. So a typical performance curve would be like this. You have an MPI program which you've written and it doesn't scale beyond a certain point. You rewrite it in MPI plus OpenMP. That incurs a bunches of software overhead, so there is a performance degradation at the start. However, it allows you to scale to higher process counts. Okay, at some point you start to scale better. This is your hope. So the potential advantages of MPI plus OpenMP are reducing memory usage, and that's quite a big one. A lot of people do it for that, quite irrespective of performance. Exploiting additional levels of parallelism, reducing load imbalance, or reducing the communications cost. And we'll cover those in turn. So reducing memory usage, some MPI codes have a replicated data strategy. Now this might be, it's a long time, in the very early days of parallel computing, when we were running on 2 or 4 processors, people would often just wouldn't do a domain decomposition at all. They would replicate the data on each process. That is no longer done typically because you run out of memory. It doesn't scale beyond a few processes. However, there are many codes where you have multiple copies of a major data structure. For example, you might have a lookup table. You'd be doing some molecular dynamics simulation where you have a large database of force fields or something. You might have produced an array which gives you the force between 2 molecules. But you might have very, very large data structures which you've pre-computed, which are static. And it seems crazy. Imagine you have a very, very large lookup table, for example, force fields or something. It seems crazy on ARCHER2 to have, if you run 128 MPI processes, you have 128 copies of that data structure, which never changes. That seems a bit bonkers. You might say, well, I don't have any replicated data, but actually you do. If you do a classical domain decomposition, as we illustrated yesterday, halos are replicated data. Halos are explicitly copies of data which are owned or updated by another process. MPI itself can consume significant amounts of memory. MPI has to maintain all these message queues and all its own data structures. If you do the default on ARCHER2, you'll have 128 versions of the MPI library running on your node. That might use a lot of memory. If you had a mixed code, an extreme, you had 1 MPI process per node and 128 threads, all the data structures could be shared by multiple threads. And all the intra-node messages, if you're sending, you would no longer need messages for them. You would only be sending messages between nodes. And this is becoming increasingly important because one of the defining features of high-performance computing at the moment is the number of CPU cores is going through the roof. Our first system, Hector, Hector back in the mid-2000s had dual core nodes, and then we went to quad core nodes. Archer, the predecessor to ARCHER2, had 24 cores per node. Now we have 128 cores per node. So the number of cores per node, the parallelism, the multi-core parallelism is going through the roof, but the amount of memory is not. Memory is expensive and power hungry, and so we're tending to get less memory per core. The amount of memory per core is not likely to increase, and so saving memory is becoming increasingly important. So just looking at the halos, as you scale to large numbers of processes, your local data structures get smaller, your local domain gets smaller, and actually the amount of halo data does decrease as the local domain size decreases, but it becomes fractionally more. You get this surface to volume effect. So for example, if you have a 50 cubed domain, and this is even worse with deep halos or greater than 3 dimensions, but I'm taking a 3-dimensional problem here where the halos are only of depth 1. If you have next to nearest neighbor interactions, your halos might be of depth 2, but here we're just thinking about nearest neighbor interactions. Then the halo size is 52, your actual array is 52 cubed. So the halo is about 11%. For a 20 cube data set, the halo is 25%. For a 10 cube data set, the halo is getting up to being about half your data. So the important point is, if you did hybrid MPI+OpenMP, you would have a much larger MPI domain size on each node, and you don't need halos for the inter-thread communication because threads can the reason that you need the halos is you can't directly read and write to a different process, but threads can. So threads can just read the data of the next thread along. So you don't need these temporary copies. So that's just saying that memory can become an issue. The other one, exploiting the additional levels of parallelism. Let's say, for example, I was doing a simulation of the energy efficiency of houses. So I have a model which simulates models how energy is used by a family in a house: heating, lighting, cooking, ventilation, all these kind of things. That could be a very, very, very complicated model. and it might be very difficult to parallelize using MPI. So what you might say is, okay, what I'll do is I won't parallelize that. I'll just have each MPI process will simulate a single house. So if I have 100 houses, I run on 100 MPI processes. Each MPI process will simulate a fixed number of houses, 1, 2, 4, 8 houses. If I have a village of 1,000 houses, I then cannot run my MPI program on more than 1,000 MPI processes, because I can't parallelize within a house. However, OpenMP parallelization is much more flexible and easy than than process parallelization. So it might be very easy to parallelize the calculation within a house using OpenMP. OpenMP is a loop-based thing where you basically parallelize loops in turn, and so that would allow you to say, well, you know, I can now run on. I can now give a different house to each node. I can run 100. I can run on 1,000 nodes, which is 128,000 CPU cores. So you've increased the scalability, potential scalability of your problem of 1,000 houses from 1,000 CPU cores, which is about 8 nodes, to 128,000 CPU cores, which is 1,000 nodes. The other one where I don't think, apologies, I don't think I have a diagram, but I will. I'll mention it because it came up in conversation yesterday. Can people see this whiteboard? Is that showing okay? Just to check. Sometimes the whiteboard can be quirky. Yeah, fine. So the other one is Fourier transforms. So imagine I have a 3D array. I'm very bad at drawing, and I want to do a parallel Fourier transform on that array. Well, by far the simplest thing to do is to simply split the array into slabs. Okay, so each process gets a slab of the array, and that means that 2 of the dimensions are local to a process. So a process can do an X here and a Y Fourier transform. It can't do the Z one, so there's some communication there. But what you've decided, when you wrote your program, you said, I am going to use this parallelization strategy. I am going to parallelize across processes in 1 dimension. So this would be on 1, 2, 3, 4, 5, 6. That would be on 8 processes. You have 8 slabs. The problem is, if I have a 512 by 512 by 512 array, or 1,000 by 1,000 by 1,000 array, that means I cannot run on more than 1,000 processes, because my parallelism, I have limited parallelism, and because I've only parallelized across the Z dimension here. Now, of course, you could say, well, you need to parallelize across another dimension, which would involve splitting another. But this assumption could be baked in right from line 1 of your code. It could assume this slab decomposition. And when you wrote your program, you thought, well, I'm never going to need to run on more than 1,000 processes. I'm happy. But now you do. What you could do is you could run you could still run on 8 MPI processes, but you could use OpenMP to parallelize the 2D Fourier transforms themselves. And so that means, again, if I have well, actually, in this example here, 8. If the domain is only of size 8, then this can't run on more than 8 processes, but it could run on 1,024 CPU cores on ARCHER2, because you could give each slab to a different node, 1 MPI process per node, and parallelize the XY slab Fourier transform using threads. So that's an example that we have. Now, as I said, the real solution is to go to what people call a pencil decomposition, which is to say, well, I will decompose in this second dimension as well. So each process now has these, what you call, so I've drawn that really badly, pencils. But that might be very difficult to do. So often there may be design choices you made early on in your code which limit the parallelization, parallelizing over a fixed number of houses, or parallelizing over only one of the dimensions of your array. So as I said, in principle, you could do it using MPI, but in practice, this may be hard. It may be hard to work around design decisions in the original MPI version. Also, the lower level parallelism may be very hard to load balance. For example, potentially load balancing, if I think about the way that I'm looking at the heat efficiency of my house. That might be a very load imbalance calculation. However, OpenMP has built-in mechanisms for dealing with load imbalance. And so that again, load balance is much easier in OpenMP than it is in MPI, because it's built into the language. So it may be better to use the additional levels of parallelism with OpenMP threads, and you then take an incremental loop-by-loop approach. It might not be optimal, but it's fine. Obviously, as I said, OpenMP parallelism cannot extend beyond a single node, but this is probably enough. As I said, you know, on ARCHER2, this gives you an additional factor of 128 threads. So that's a large factor. So in fact, the fact that you can't do OpenMP between nodes doesn't really have any effect on any implications for how much this will benefit your scalability. So load balancing between MPI processes can be hard. The main problem is that transferring work also involves transferring data. And often you may say, well, actually, you know, it may not be worth transferring small tasks. It may be more effort to give someone else a small amount of work than just do it yourself. And you may have to have you may need to restrict it. You would like to have a global view of all the work across your processes and evenly balance the load. That may be hard. So you may have a local, they're called a diffusion algorithms. You may only transfer the load locally. I've got too much work. I've got more work than my neighbors. I'll give them all a bit and let them work. But load balancing is very difficult. And particularly the more processes you have, the smaller the amount of work they do, the harder the load balancing is. It's much harder to get 1,000 people to work efficiently than to get 10 people to work efficiently. And so if you load balancing between threads is much easier because you only have to transfer the tasks, not the data. All the threads can read and write to the same data. And also, as I said, there are load balancing mechanisms built into frameworks like OpenMP. So for application with load balance problems, keeping the number of MPI processes small can be an advantage. This is why actually Josh's application came to mind, because it does both FFTs and has load balance problems. But I don't know if this is that you're using Python, that might be challenging. Also, you may reduce communication costs. It seems natural to imagine that two threads with a node would be able to read and write data faster than MPI could send data, because MPI probably has to do some copying into buffers. However, that's not a big issue. And actually, it's really the bottleneck. As I keep saying, there is no point optimizing something which is not the bottleneck. Okay, the bottleneck in MPI is inter-node communications over the network, not intra-node communications. And so, you know, you may be able to speed up your intra-node communications using OpenMP, but that might not help because you still have the inter-node ones. Some cases, though, there are cases where MPI codes communicate much more data than is actually required. So if your communication pattern is data dependent, then actually it can be, then the OpenMP can help you. And this is something which the we'll come back to it. Sorry, it's the next one. Collective communication. This used to be an issue. So for example, early on, when the fact that the HPC systems have become clusters of shared memory nodes, some of the MPI implementations weren't optimized. And so if you were doing an all reduce, for example, it was actually worth doing it by hand. So you would do the node local part using threads and then accumulate across processes using the native all reduce. Those days are probably well past. Most MPI implementations are very, very aware of the shared memory nature of your nodes, and they will do this automatically. So I would not. It's fun to play around with possibly, but it's not really a motivating case now. So the example is from the European Centre for Medium Range Weather Forecasting. They have a model called the IFS, Integrated Forecasting System, I think it stands for, and basically they have something called semi-Lagrangian advection. I mean, basically, it's if you're simulating the weather over a region of the United Kingdom, then you only need there's a wind blowing. Okay, so you don't need data from processes that are downwind. You only need data from processes that are upwind. That's where the data is coming in from. Okay, so basically you only need to transfer data along the direction in which the wind is blowing. So for example, if the wind is blowing east, I need to know I need to get data from my processor to the west to tell me what's coming in. I need to send data to my east process, but I don't need to get information from them because the wind is blowing in a particular direction. However, that is very, very, very difficult to do in an MPI. It's very difficult to say, look, the wind is blowing east. I'm not going to send data to my west neighbor, because how does the west neighbor know I'm not going to? You get into a kind of a catch-22. It's very, very difficult to do or efficiently do data transfers which depend on the to do message passing depending on whether the data is what the data is. What you can, they used a hybrid MPI+OpenMP approach, which has a significant reduction in communication and a significant reduction in memory. So they have a situation where if this is their decomposition, where they have processes, this is a 3x3 grid of processes, for example, simulating the weather. They have quite deep halos. So this process needs all the data in principle from this large extended region. I've drawn the halos of depth 2, but in fact they can be up to a depth 7. And if the wind is blowing in this direction, I only need information from these data points here. However, in the MPI implementation, I will collect data from all these data points because the code just swaps the halos. If you were to not have a 3x3 grid of MPI process, but have one MPI process doing all this, and use a 3x3 grid of threads, the threads could just read and write the data they want. And that's what they did. And it led to a significant reduction in the amount of memory, because you need we saw that the relative overhead of halos decreases as the arrays get larger, but also a significant reduction in the volume of communication. Having done that, I did want to sort of put you off a bit, talk about the problem with MPI+OpenMP, and these fall into sort of 4 categories: development and maintenance costs, portability, libraries, and the performance pitfalls. So the one which I think is the biggest issue is development and maintenance costs. In most cases, developing and maintaining hybrid code will be harder than a pure MPI code. Although OpenMP programming is probably easier than MPI, it's still parallel programming. And to maintain this program, you need programmers who can do both MPI plus OpenMP. OpenMP is subject to subtle race conditions and non-deterministic bugs because you can read and write to the same data. You can get different answers depending on who gets there first. So correctness testing can be hard. Portability, well, MPI and OpenMP themselves are highly portable, but not perfect. But the combined one is less so. And the main issue is thread safety. We'll come across this in the next lecture, but MPI was written in a world where you had one process running on one processor with no threads. So MPI is not itself thread safe, and that does have issues. And if you program in a style, which we'll come across in the next lecture, which requires MPI to be thread safe, that may preclude you from running on certain platforms which may not have a thread safe MPI implementation. Also, you'd like to make sure the code functions correctly as a standalone MPI code, and that might be quite hard. Also, as a standalone OpenMP code, that would be even harder. But you would like to be able to compile a pure OpenMP, a pure MPI, and a hybrid code from the same source code base, but that can be very difficult, and that is an additional maintenance overhead. This is a bit of a kind of a pragmatic issue, but there is a big issue here if you use libraries. So people do use libraries all the time. You use Fourier transform libraries. You use linear algebra libraries. Okay, so if the pure MPI code uses a distributed memory library, you need to replace it with a hybrid version, and there may not be a hybrid version. Yeah, so you may say, look, I'm running a hybrid MPI OpenMP. I now call the linear solver or FFT. I need that to be hybrid as well. I need that to use OpenMP threads to use all the parallels. That may not be enabled. The other problem is that if you have a pure MPI code, if the pure MPI code uses a sequential library, then sorry, I've slightly jumped ahead of myself. So if your MPI uses a distributed memory library, that's a parallel MPI library, like a parallel Fourier transform library. It needs to have a threaded version. If your pure MPI code uses a sequential library, which might be for a local FFT, you need to replace with a threaded version or a thread-safe version. We'll come back to this later. But the big problem comes actually if what often happens is you get too much parallelism. What can often happen is you have a hybrid MPI OpenMP code, so you have lots of threads. These threads call a Fourier transform or a linear algebra library, though internally that linear algebra library may also spawn its own threads. And so you can end up with oversubscription. You can end up running thousands and thousands of threads on a machine with only 128 CPU cores. So if you're calling external libraries, it can be quite challenging for a bunch of reasons. The final thing is performance pitfalls. Adding the OpenMP code introduces an additional overhead not present in the MPI code, and we'll talk about these in the next lecture. But the other issue here is a tunable parameter. I give you an MPI code and tell you to run on 8 nodes of ARCHER2. What you do is you run 1024 MPI processes, 128 per node. If I give you a hybrid MPI OpenMP code and tell you to run it on 8 nodes of ARCHER2, you have a huge number of possibilities. You could run the pure MPI code, 1024 MPI processes. You could run 512 MPI processes and 2 threads per process, 256 and 4, 128, 64, 32, 16, 8. So you've got 8 possibilities, combinations of processes and threads, all the way from 1 MPI process per node and 128 threads through to the pure MPI code, 128 processes per node and 1 OpenMP thread. And that means that every time you go to a new platform or use it or study a new data set, you have to do this scan of what the best combination is, and it's hard to guess the right value without experiment. Also, we now care about the placement of MPI processes. If I'm running 8 MPI processes on an ARCHER2 node, I want those processes to be spaced out by 16 CPU cores, and I want those gaps to be filled in by the OpenMP threads. That can be challenging to do, and you don't have to care about it. So there's a lot of pragmatic issues with this. The main issue, though, I see is that it's Amdahl's law. Amdahl's law says that the performance of a parallel program is limited by its serial component, and that's often things like I/O and other serial operations. The problem with an MPI plus an OpenMP code is that you will have serial sections in your OpenMP code. So imagine I have a machine with 6 CPU cores on a node. In MPI, I run 1 MPI process per CPU core, and they run all the time. If I decide to do hybrid MPI plus OpenMP, I only run 1. So some people think that the model is that you're running 6 MPI processes, which then become 6 threads. That's not what you do. What you do is right from the start, you only run 1 MPI process. You run a single MPI process. And that means that anywhere where you're not using OpenMP, you're wasting all these CPU cores. And the problem there might be that you actually have you might have a computational kernel which goes a lot faster in hybrid MPI OpenMP, like a Fourier transform. So you want that to be parallelized, but to stop the code slowing down because of Amdahl's law, you have to parallelize every loop in your code with OpenMP, even if those loops or those sections of code were perfectly okay in pure MPI. So if you have a hybrid MPI OpenMP code, you have to put OpenMP everywhere. Otherwise, you're not using up all the parallelism within a node, even if you only really need it for performance reasons in one place. And this is something which people often forget. More pitfalls. There's bunches of stuff here to do with the way that OpenMP works, but I'll cover these in detail in the next lecture, really. The one other thing is number effects, non-uniform memory access. modern CPUs, I say that an ARCHER2 node is 128 CPU cores in a shared memory node. That's what it looks like logically, but underneath it's much more complicated. It's actually, ARCHER2 is actually 8 mini processors of 16 cores all stuck together. And at that level, you have non-uniform memory access. Although different CPU cores can read and write to the memory of all the other CPU cores, it's much quicker to write your own memory than another person's memory. And you can get things called NUMA effects, non-uniform memory access effects, where your program runs slow because the memory you're accessing is not local to you. It is belongs to somebody else. So Sean, you had a question?
Hi, yeah. Is it possible to pin an MPI rank to a single NUMA domain? So I guess the idea is that I'd want to have one MPI rank on a single socket and then exploit all the parallelism with OpenMP, therein.
Yes.
So like I'd have one node, 4 sockets, and how easy is it to pin to make sure that I get like exactly, the MPI gives me exactly one rank on one NUMA domain.
So on ARCHER2, it's very easy. You just say, so actually, I'm going to I'm going to log into ARCHER2 because it's a very good question. Actually, it's something I meant to. Where are we? TA 25325. So on ARCHER2, it's easy. It may be difficult on other machines, but I'll share this. I'll share this because this is something which will come up, of course, later. Can you see my yeah? So there is a program called XT-high which does nothing but print out where it's. So the question is, yes, you can pin processes. But the problem is, how do you convince yourself that it's correct? Yeah, and the worry is that if you get it wrong, you get terrible performance. So you really want to have a program which prints out. And the ping pong program does that. So if I run the ping pong program, okay, error, what's wrong with these two processes? It's a bit annoying. Okay, let's, if you look at the ping pong program, the ping pong program has, and I just stole this code from XT-high. Sorry, it's utilities.c. No, location.c has a program called location.c, which basically print location, prints out where each rank is running. However, if we do something like, let's run 8 tasks per node, and we'll run XT-high. So XT-high is your friend. So you're talking about on ARCHER2. ARCHER2 is basically, actually, it's got 2 sockets. It's really, I think it's effectively 8 NUMA domains. Yeah, within a socket, there's also quite a lot of structure. Yeah, so what I would do here is task per node equals 8, and CPUs per task is the key thing here. That is the gap between the processes. So I think that will place the tasks on 0, 8, 16, whatever. But this CPUs per task is your friend. Yeah, this is the thing which does it. So on ARCHER2, processes and threads are bound by default, but the question is getting them bound correctly. And unfortunately, there was a change recently where you have to do this silly magic here. This is not exported to SRAM like it used to be. So it's all a bit annoying, but let's SBatch that. Running. And So there, do you see? It says that node 0, rank 1 is bound to affinity 16 to 31, which is so you can see they're bound to the NUMA regions. Does that answer your question?
Yeah, so is that I guess 0 to 15 is one core with the first core or something, isn't it?
It's the first. So the CPU cores are numbered linearly 0 to 127, and I believe that they're actually arranged in 8 NUMA regions. 8. They're called chips. I can't remember what they're called. There's a very complicated hierarchy, but yeah, CPUs per task is your friend here, and XT high is your friend. It tells you what's actually happening. So that affinity says it will only run on cores 0 to 15. Yeah, does that make sense?
Thank you so much. Yeah.
Yeah, fine. Yeah, so that's a very good question, and I will go back and share the PowerPoint. So NUMA effects can limit the scalability of OpenMP, and it's a technical reason, but in fact you would not expect your hybrid MPI OpenMP code to scale beyond the NUMA region. That is very difficult. So on ARCHER2 you would expect the scalability of your OpenMP section to be limited at 16. You may be lucky, but that was so. It may be advantageous to run one MPI process per NUMA region rather than one MPI process per node. Yeah. So the hardware. Someone's posted the hardware link. I always find the hardware very, very difficult. Yeah. There's a nice diagram there. Yeah, the NUMA regions are 16 cores. There's a sub hierarchy of 8. But the NUMA regions are 16 cores. Yeah, that's correct. There's other effects which I won't. Whoops, sorry, I've hit the wrong. Sorry, I've hit the scroll. So we've done this. New effects. So process and thread paper. Well, here we go. On NUMA nodes, you need to make sure that the MPI processes are spread across sockets, and the OpenMP threads are on the same socket as their parent process. And not all batch systems do a good job of this. But ARCHER2 is set up to be reasonably good. But XT high is a really nice piece of code, and it is pretty portable. A colleague, Kevin, maintains a version which if it's not installed as a module, I just compile up and run as a matter of course. It's here. So yes, thanks, Josh. There is actually a hierarchy. There is a sub hierarchy below the NUMA level, but you don't tend to see that. So I think the right conceptual model to have of ARCHER2 is each node is 8 mini shared memory processors of 16 cores. That's a reasonable model. So there are 4. I'm going to finish very soon. There are 4 styles of MPI+OpenMP programming, depending on when and how you call the threads, and each has its advantages and disadvantages. And we'll see that these 4 styles are actually implemented in MPI. MPI now has a threading interface, which is to be used in conjunction with OpenMP, and you can query MPI as to what level of thread support is available or that you're using. So the 4 styles are master only. All MPI communications takes place in the sequential region of the OpenMP program. So in this case, it's as far as MPI is concerned, you're just running a serial program, a normal program. There is no real effect. All that happens is that the calculation parts of your program go faster. Funneled is all the MPI communications take place through the same master thread, but can be inside parallel regions. Serialized says only one thread makes MPI calls at any one time. However, different threads may be calling the MPI library at different times. And multiple is all bets are off. And multiple says any thread can call MPI at any point. And I will just outline the master style. I think it's now probably called something different than master because of unfortunate terminology. So basically, it's really quite simple. You have an MPI program in C or Fortran where you have work, communications, and work, you speed up the work with OpenMP, but you leave the communications absolutely untouched. And for this to work, you don't actually need any MPI, any thread safety at all in your MPI library. As far as the MPI library is concerned, you're running a serial program on each node, and so that really is the simplest one. And it's actually quite straightforward to do. You take your program, you speed up the parallel, you speed up some of the loops, but you leave the communications as they are. So that's the obvious place to stop, and then we can basically look at the exercise, and then you can play with it. So I will now go back to the exercise on the sheet. So the exercise is based on traffic modeling. If you've done my MPI course, you'll have seen this. You'll have seen this, but I will just. So I mean, this has a bunch of. This actually comes from a larger course, which has a bunch of MPI exercises, a bunch of OpenMP exercises about hybrid MPI OpenMP. I mean, I would say probably just jump straight to the hybrid MPI OpenMP, but if you're interested, then you can do the other ones. But I already had a hybrid MPI OpenMP example here, and it actually starts off by running XT high, which is something we've already talked about. But I will just show you how to get this. So traffic modeling, code and solutions, there we are. So you could just, I use wget typically. So I'll just spend 5 minutes talking you through the code. So there's a lot of stuff here, but if you go to the C serial, it's a very, very simple cellular automaton, incredibly simple cellular automaton, simulating traffic. And all it does is it fills a road with zeros or ones. A one is a car, a zero isn't a car. And every update, it tries to move a car forward if it can. So cars move forward if the space ahead of them is clear. Otherwise, they don't move at all. So there's quite a lot of setup here, but basically, I loop over a number of iterations. I set some boundary conditions, and I have periodic boundary conditions on my road. I update the road, and I copy back. An update road is where is it? It's in trafficlib.c. Update road does nothing but, it's very, very simple. Loops over the road. If the old road has a car, if the cell ahead is full, it doesn't move, else it moves, and you look down the way. If the cell behind you is a car, then so if you're currently empty, this is saying if the cell currently has a car, does it move out? And if you don't have a car, is there a car downstream from you to move into your cell? But it really is, the reason I use it is it's a very simple program where it's a 1D program where the update equation are such that the value of each cell depends on the value of its neighbors. Oh, sorry, something weird has happened. So sorry, I shared this terminal and it stopped. I'm sorry about that. So apologies. Something very weird has happened. It says I'm sharing, but I'm not. Sorry about that. Okay, so I'll go back to the start again. So what I did is I went to the website and cut and paste the URL of the traffic example, and I did wget the traffic example. I can then unpack it. And you see there's lots of stuff here, but you have to follow it through the exercise sheet. But I was just showing how the model works, and the serial code. It basically, you have an integer array which represents a road, and each iteration you update the road, and it's a very, very simple cellular automaton. So we've got update road from the new road as a function of the old road. You loop over the old road, and the old road contains ones or zeros. A 1 means it has a car, a 0 means it doesn't. So the update rule is, if you currently have a car in cell I, it can't move forward if the cell up the way is occupied, else it can move forward. Else, if you're currently empty, if there's a car down from you, it moves into your space, else you stay empty. So it really is almost the most simple model you could imagine. And bizarrely, there is actually a if you want I can never find it on Wikipedia. Rule 184. So if I share, if you go to Wikipedia, sorry. So something that, apologies. Okay. If you go to Wikipedia, if you're interested, it's called Rule 184. So it's a very it's an almost trivial cellular automaton. Quite bizarrely, there's a whole Wikipedia page about it, but that's what the code does. But the important point for our purposes is it's a very simple code where the update rule for a particular grid point depends on its two nearest neighbors. And that means that to do it in parallel, you just do nearest neighbor halo swapping. So the obvious thing to do is to just parallelize that loop. And if I show you the, is to parallelize the update loop, but to leave the MPI as it is. So if I again share back to my, this is the serial code. If you look at the parallel code, you'll see that basically it does exactly the same thing. It's a lot of setup here, but the roads are n+2 because of the halos, and then the update route is basically you loop over, you do the update, but before you do the update, you have to do a halo swapping, and you have to do the number of moves. Remember, this is a very poor way of doing the halo swapping, but hey ho, that's the way it is. So the obvious thing to do to parallelize this code with hybrid MPI OpenMP would be to parallelize that function and to parallelize that function as well. And if you want to see how they're done, there should be an OpenMP version, which you can, so it's a matter of basically sticking the two versions together, where you'll see that I parallelize the copy back with the OMP parallel 4, but maybe more interestingly, I copy the update road. I parallelize with a parallel 4 as well. So the exercise is really kind of sticking the hybrid and MPI together, but you'll see in the sheet there's also quite a bit about process placement, because actually without correct process placement you're not going to get any performance at all. So that's you know, that's, and we're also going to use this for shared memory as well later on. But that's the exercise sheet. It fundamentally ends up doing hybrid MPI OpenMP. But if you're interested, you could actually just play around with the MPI code. You could just play around with the OpenMP code, or you could stick them together. So are there any? So the timetable is that we work on that for the next half hour, then have a coffee break. So the basic fixed point is my next lecture. So the main thing is, I will next lecture is at 11:30, but I will be around for the BST. I will be around for the next. I'll be around here for the next 30 minutes to help you if you have any issues with the exercise. But I will be taking a coffee break myself from 11. The next lecture at 11:30 is the sort of the next fixed point. Are there any questions about that? So I sort of gave you a lot of pitfalls and whys and wherefores. The next lecture will actually look at how we do these things in practice, how we actually add MPI and OpenMP together in these 4 different models of master only, serialized, funneled, and the all bets are off one. I can never remember what it's called. Sorry, my term. Multiple. Okay. Adele, yes, Adele, so very briefly, do you want to log on and I'll give you a TOTP code? Is that okay? Adeleki has a time skew on his. I don't understand why, but on his TOTP authenticator, but it works on mine. So, are you logging on just now, Adeleki? I can give you a code just now. It is 184. So just wondering if that worked for you. That's 184.459. It's about to run out, but it should. Brilliant. So that should persist for the whole, unless you change networks, that should persist for the whole day. So you shouldn't need it anymore. No problem. There's a question about, okay, IO. So that's a very good. So it's a good question. It's a complicated question. So can you, so Sharon, can you, I mean, you can go to breakout room, but if it's in general, can you just outline what your IO problem is? I think you mentioned this yesterday, just a higher level, kind of understand what you're trying to do. Or what's your current IO strategy, I guess, with my question. Okay, fine. So it's complicated. So doing IO from every process is bad because it totally overloads the parallel file system. So, you know, if you're running on 16 nodes, which is whatever it is, 60 times 128, I can't work it out, whatever that is, you know, 20,000 MPI processes, the file system cannot cope with you opening tens of thousands of files at once. It's just going to fall over. So you want to avoid doing one IO transaction per process if possible. However, unfortunately, for reasons I don't really understand, the IO from a single process on ARCHER2 seems to be throttled about a gigabyte a second. Now, if you're running on tens of nodes, that's fine because you will get tens of gigabytes per second. But if you're running on, say, 8 nodes, then you might want to have multiple So the best thing to do if you're going to implement this in the code is to have a sliding scale, allow you to find the sweet spot, basically. You may find best performance with 120 MPI processes writing file IO, but you're killing the system for everyone else. So I wouldn't want to do that. But I would, yeah. One, if you have enough nodes, then one is the best. If you have, if you don't have many tens of nodes, then you might want to consider more than one IO process per node. Does that make sense? I don't understand why it's a feature. So no, I mean, so what MPI+IO does is MPI+IO. I mean, MPI+IO basically doesn't do anything magic. What it does all the coordination for you. So you can tell MPI+IO, look, I've got a 3D distributed array distributed across a 3D grid of processes. Could you please write it out in the correct order? It does it all for you. It sorts out all that. However, what it is doing is it is nominating a subset of the node. Well, it's nominating a subset of your MPI processes to be, they call them aggregator nodes, your IO processes. So it will nominate a subset, and you don't know which, but a few tens probably of your IO, of your MPI ranks to be IO processes, do all the gathering of the data to the correct processes, and then write it to disk. So there's nothing magic about it. At the end, it's just calling fwrite, like you could, but it is parallel because it does not write from a single process. It will nominate a bunch of IO processes. It will also match those choices to the file system, so it will pick the right nodes to do the right IO. But I mean, the fastest way to do IO is to get every process to write to disk. That is the fastest way to do it. But the problem is, you end up with garbage on the disk. You end up with trillions of little files, and also you kill the file system. That kills it for everybody. So MPI+IO is, at the end of the day, some process somewhere is just calling it open fwrite close, but it's the fact it does all the aggregation for you, which is the good thing. Does that make sense? Well, the problem actually, hand rolling is really quite difficult, to be honest, because you have to also, it's not just hand rolling the software, you have to consider how best to use the local file system, be it Lustre or something like that. And that's quite a lot of tweaking. So you might write a hand rolled one that works really well on ARCHER2, then you get the next system that's terrible. So I would really not recommend hand rolling, I have to say. But you're right, it's not better than hand rolling, but I would advise against hand rolling, I have to say. Yeah, that's a good question. Parallel IO is quite complicated. Yeah. So let's do a quick recap of I don't quite understand why it's not letting me do. Anyway, doesn't seem to want me to do a. Oh, there it is. Okay, fine. I've got it there. So there are 4 styles. As I said, master only, where all MPI communication takes place in the sequential part of the OpenMP program. So as I said, that means that as far as MPI is concerned, it's just a normal program. And what you see is that your computation parts go faster. Funneled, I'll have examples of these later on. Funneled is all MPI communication takes place with the same thread, but can be inside parallel regions. Serialized is where you still say that only one thread is calling the library at one time, but you, the programmer, say, look, different threads can call the library, but they will never do it at the same time. So in that case, it's up to you as the programmer to make sure that you abide by this. But you're saying only one thread will make an MPI call at any one time, and we'll see that there are some issues with that in the examples. And multiple is the all bets are off. MPI communication happens simultaneously more than one thread. As I said, some MPI implementations don't support this, and those which do mainly don't perform well. And we'll talk about that when we get to the relevant slide. So OpenMP master only, as we've seen, you just have a program which does work, halo swapping, for example, and work, and you accelerate the work here, and you therefore, but you don't do anything with the communication. So the communication is entirely outside the parallel region. So OpenMP will spawn multiple threads here, but at the end, only thread 0, which is identical to the parent process, carries on. So as far as MPI is concerned, this is just a normal program. It doesn't see anything funny at all. Funneled here, as I said, funneled is again, you guarantee that only the master thread calls calls the MPI library, but it can be within a parallel region. So what you've got here is you've got an extended parallel region which includes the work, the send, and the work. That means that you therefore have to put barriers in, because you want to make sure. Now remember that the end of the parallel region is effectively a barrier in the sense that the parallel region doesn't finish until the threads have finished. Okay, but if you have an extended parallel region, you need to put those in for yourself. So you need to say, well, before I do the MPI send, I need to have completed the work, otherwise I can't send it, and I can't do the next section of work until this is completed. So you need a barrier here and a barrier here. And what we're saying is, you, the programmer, have said that only the master thread will do the communications, and so you put a hash pragma OMP master there. So all the threads are executing this region, but only a single thread, the master thread, will call the send, and the barrier is needed because master doesn't have a barrier at the end. Serialized is where you again, we have work. But in this example, we're saying, well, actually, as soon as any thread has completed the work, it's okay to do the message passing. So what we're going to do is we're going to say that the threads can do the message passing as soon as they get here, but we need to make sure that only one thread calls the MPI library at once, and that can be done quite simply in OpenMP with a critical region. A critical region is a region of code which only a single thread is allowed to be in at any one time. And so this would, I'm trying to get my cursor back. This would ensure that. So if you didn't have that, then you would not be having the serialized model. You would be having the more general multiple model. Here's the multiple. You just have work, then everyone calls the send, then you have work. So this achieves the same as that. Okay. However, it does it in principle, allowing every OpenMP thread to call the MPI library at the same time. So what does thread safety imply? Well, making MPI libraries thread safe is difficult. If MPI were defined today, it would probably be defined with threads in mind right from the start. But when MPI was defined back in the early 90s, not only threading wasn't that common, multi-core processors weren't really around. In fact, one of the design choices for MPI, let alone being thread safe, was to allow MPI to work correctly on a system which did not have threads at all. In other words, where there was could only be running a single program all the time. And that is why MPI has this model where it effectively uses, as we said, every MPI call as a manual interrupt, because one of the design goals was to allow it, far from running on a threaded processor, to run on a processor which had a single core and no threads at all. So what will probably happen is that people will retrofit thread safety onto their MPI library. And so you have two possibilities. One is you keep the same structure and you lock access to the data structures. So every time you have access to the queues, for example, you're updating a queue, you basically lock access to make sure that the threads don't conflict with each other. So you don't really have a parallel MPI library. You're just saying that the library isn't taking advantage of the parallel threads. It's basically just making sure they don't interact with each other. Or you have multiple data structures in one thread. There's lots of things you can do. However, this adds significant overheads. Now, you may want that. However, you would be very, very annoyed if you ran a program today on ARCHER2 and it ran at a certain speed, and then you ran it on Monday and it ran half the speed, and you looked up the manual, oh, we've just made the MPI library thread safe. So all this thread safety, locking, and potentially more complicated code will slow your MPI code down. But you don't imagine you don't want threading. Your code is going to go slower for no benefit. And so MPI defines, because adding thread safety potentially and practice probably does add overhead to the MPI library. I'm just checking I was recording, sorry. Then when you initialize, so MPI defines various classes of thread usage. So what you do is when you there's a new initialization routine, not MPI init, but MPI init thread, where you say to MPI, I want this level of thread safety. And that allows you, for example, to request the library which has no thread safety. In other words, it's just the standard MPI library, and that will therefore give you no overhead. In fact, MPI, you can still call MPI init, but it's important that you don't want the whole MPI library to be implemented with thread safety, because that will slow things down, and you maybe don't want that. So MPI init thread is the new initialization routine, which you are supposed to use if you call MPI+OpenMP. I actually very rarely call it, because I typically use the master only model. And in that case, you don't need any thread safety, so you can just call MPI init. I should probably technically call MPI init thread, but I've never seen a problem. So MPI init thread works in a similar way to MPI init. Initialize MPI on the main thread has two arguments. You say what level of thread safety you want, and MPI tells you what level it can provide, and that may not be the same. Okay, so you ask for a thread safety level, and it tells you what it's provided. So MPI init thread. Int required, int star provided. And what you're supposed to do is to check that the MPI library can provide the level of thread support that you require. So MPI init thread, there are four levels of thread safety. MPI thread single is only one thread will execute. That is saying that I've just got a normal MPI program. So I don't actually need anything from the MPI library at all. Then there's MPI thread funneled, which says the process may be multi-threaded, but only the main thread will make MPI calls. All MPI calls are funneled to the main thread. MPI thread serialized, which I said the process may be multi-threaded, and you may have multiple MPI calls, but you, the programmer, are guaranteeing that there's never a clashes. MPI calls are not made concurrently from two distinct threads. An MPI thread multiple says that there are no restrictions. Now, you might note that actually I'd identified 4 types of parallel hybrid MPI OpenMP: master, funneled, serialized, and multiple. But MPI only has it doesn't have master. It doesn't have master. It has funneled, serialized, and multiple. The reason is that the MPI library is not talking about OpenMP yet. It's talking about general thread support. So the MPI library has been written to be callable from a general thread model, which could be POSIX threads or C++ threads. And so actually the OpenMP terminologies, there isn't 100% mapping onto the MPI terminology. But actually what it means is there's no distinction between master only and funneled. Basically, all the MPI library cares is that only a single thread, that all the MPI calls are made from the same thread. And in OpenMP, you can achieve that through master only or funnels, but the MPI library doesn't really care. So the integer, these values they're called MPI thread single, MPI thread funnels, MPI thread serialized, and MPI thread multiple, and they are integers which are arranged in order. Monotonically in order. So basically you can compare, you might ask for MPI thread multiple, and the MPI library might say I can only do MPI thread serialized. So you could check if provided is not equal to requested, or if provided is less than requested, then there's an issue. So what you really ought to do when you call MPI MPI query thread returns the current level of thread support, but it's also what you got from MPI. So when you do MPI init thread, you should get, if provided is less than requested, not a high enough level of thread support. I mean, some programs might do opposite. Some programs might have different implementations where some of them are thread multiple, some of them are thread funnel, some of them are thread serialized, and you might switch on that. However, to be honest, the normal approach is you assume a certain level of thread safety. If it isn't available, you just, you're dead in the water. So you really definitely should check. I would do it at the MPI init thread stage. If provided is less than required, then print, there's a problem here. However, you can actually query the level of thread support at any point. So, the different styles, what are their pros and cons? Well, master only is simple to write and maintain. There's a very clear separation between the outer and the inner levels of parallelism. And there aren't any concerns about synchronizing threads. So basically, because by the way that you write the OpenMP, all the MPI calls take place in serial regions. So as I said, all the OpenMP is doing is accelerating the computational parts. So that's very nice. Simple to write and maintain. You can basically run it on any number of threads pretty safely. You only have to worry about the thread correctness of your computation stage. You're not interested in any thread issues with the communication stage. The disadvantages are the threads other than the master are idle during MPI calls. So if the MPI calls are pretty heavyweight, that could be a poor. There's a slight technical issue that memory access speeds are terribly slow on modern computers, horrifically slow. But the reason which your ARCHER2 node or your laptop doesn't run at a snail's pace is that we have cache memory. And we typically have cache memory for each CPU core. So what happens when you run a good OpenMP program is each thread is running on a different CPU core, and the data which each thread is processing tends to reside in the CPU core, in the cache of the CPU core on which that thread is executing. So most of the time when you request data, it is already in the cache that you need. And so the program ticks along at quite a nice speed. However, if you do any serial operations on a single core, a single thread, then all that data then has to be taken back to the cache, is taken back to the cache of the calling thread. And so because you're calling the MPI process, it's a slightly subtle point, but because you're calling the MPI calls on a single CPU core or a single thread, all the data goes through the cache where the master thread is executing, and that could cause quite some overhead. Okay, you're also not overlapping inter-process and inter-thread communication. The inter-thread communication is happening through the OpenMP sections, and the inter-process communication is happening through the MPI section, but they're completely distinct. And also, the only way to the synchronization after the message transfers is by parallel regions, and the parallel regions have a relatively high overhead because they're synchronizing all the threads. Also, because you are only a single thread is calling the MPI library, if there's a large amount of work required by the MPI library, then that may be quite slow. So for example, I talked about using derived data types for non-contiguous data sections. If that may be something of an overhead to process, to inquire about and understand and interpret the structure of the MPI derived data type, this unpacking stage will be done only on a single thread. It's done sequentially, and that could have some performance implications depending on how much use you make of MPI derived data types. So here's an example. We've got a loop, do I equals 1 to n, ai equals bi plus ci, and then we're sending a n and receiving a 0, and then we're doing another loop, do I equals 1, di equals ai minus 1 plus ai. And so we've got a step, we're doing a local operation here. We've got an operation here which requires a neighboring data from a neighboring process, ai minus 1. So I store that in a0. Okay, so I'm sending this is sort of a one-sided halo swap. So here the intranode messages are overlap with the internode. Okay, if you just do pure MPI, the messages which are going inside a node between the processes on a node are being sent at the same time as the messages which go between nodes. However, if I do this, it's slightly, if I then basically have a bunch of threads, and so I am doing the entire loop over all n times n threads data points with a parallel do, then the inter-thread communication happens here. This communication is transferring, is the AI minus one AI. There's no explicit communication there, but you are reading data. The communication here is reading, this thread is reading some data which has been updated by this thread because it's reading AI minus one, so it maybe have been updated by a different thread. And so you have two, so this could potentially produce an overhead that rather than all the messages, all the data transfers happening at the same time, they're happening in two stages, depending on whether they are intranode or intra or internode communications. And also there's an implicit barrier here for the parallel do, which is a synchronization point. Funneled is where you basically have extended parallel regions in OpenMP, but you use something like a critical region to make sure that all the communications is done by a single thread. You use a master region to make sure that all the communications is done by the master thread. Apologies. It's simple to write and maintain. There are easier ways to synchronize threads before and after the message transfers because you are not you're not ending and restarting the parallel region. And it is also possible for threads to compute while the master is in an MPI call. So, while the master is doing the MPI call, other threads can in principle be doing other stuff. However, it's more complicated. The MPI and OpenMP levels of parallelism are less clearly separated, and therefore it's more complicated to maintain and make sure you get correctness. And we still have these two issues that all the communicated data pass through the cache where the master thread is executing, and we still don't get overlapping between the two different types of communication. And so OpenMP funneled, sorry, have I got the right? Yeah. OpenMP funneled with overlapping, sorry, is we basically, okay, so we have a parallel region, we have some work, and we finish the work, okay? Here I'm saying that if I'm thread 0, I do the send, else I do some computation, then I have a barrier. So what I'm saying here is that I have some work, I finish the work, I send the data, I finish sending the data, and I do some more work. However, what I'm doing is, rather than using a master region so that only the master thread executes the send, I'm doing it by hand with an if, and that allows me to do an else. Unfortunately, you can't use a work sharing directive like OMP2 or OMP4 in here because those directives, at least in the simplest form of OpenMP, require all the threads to be executing that. So that's a bit of a problem. If you want to do overlapping, you have to basically do a nested parallelism. So you have to say, I'm going to have a parallel region, but I'm going to spawn two threads at this level. Then the first thread does the execution of the MPI, else a single thread enters here. Well, but that thread can then spawn more threads. So if I was running this on 64 CPU cores, I would spawn one thread here and one thread here. But then this one, there is now still 62 unused cores, and with this nested parallelism, which is possible in OpenMP, but maybe not particularly efficiently implemented in many cases, you can eat up the parallelism with a work sharing directive down there. But again, it's this higher overhead, it's harder to synchronize it. It does get rather complicated. So serialized, the advantages of serialized are, this is where you have multiple threads calling the MPI library, but they are calling it one at a time. It's easier for threads to compute while one is an MPI call. And you can communicate, because you have multiple threads doing communication, you can arrange them to write their own data. So you can basically say, look, a thread will communicate with MPI the data which is responsible for computing. However, it's even harder to write or maintain you get a lot of small messages, which gives an additional latency latency and there's additional overheads. And then there is a big problem, okay? Because when you send an MPI message, you do MPI send, you specify a destination rank. You say, I want to send this message to rank 5. However, in the hybrid MPI+OpenMP model, there are multiple threads operating in rank 5. And so if each of those threads is calling MPI on its own, there could be multiple receives from the same rank. So you could have 8 threads all calling a receive from rank 5. You send a message to rank 5. Who gets the message? Okay. Well, it's difficult to do that, and so the MPI doesn't really support that. However, you can kind of fake it by using tags. So a standard trick in the serialized or hybrid MPI+OpenMP model is to tag the messages with the rank of the receiver. Tag the messages with the thread ID of the receiver. So you might say that you send a message to rank 5, but you tag it 7, saying this is for thread 7. But you have to do that by hand. So as I've said there, a call to MPI receive could match any message coming in, and we can. There are 2 ways you can distinguish these. One is to use different tags, or you can use different communicators. You can basically have different MPI processes, MPI threads becoming to different kind of slice-wise communicators. But it does get more messy, so it's already starting to get quite complicated. And finally, multiple, this is the easiest to write in the sense that you don't have to worry about anything. You're saying you've delegated all bookkeeping responsibility to the MPI library. So messages from different threads can in theory overlap. However, as we've seen, many MPI implementations will actually only, because they were written pre-threading, they will actually serialize internally, so they can only process them at a time. But you can still communicate your own data, and you don't have to worry anything about synchronizing threads. It's responsibility of the MPI library. However, by passing all that responsibility to the MPI library, you have put a lot of overhead on the MPI library. It will probably not perform very well. It'll probably be slow. Your code may be hard to write or maintain. And also, not all MPI implementations support this. So although it is the most general model, it may not perform very well, and it may place too much requirement on the MPI library. And if the MPI library is able to do this, it may do it in a very poor way. Sorry, it may be to do it in a slow way. So, I've gone the wrong way. Apologies. So the summary is MPI and OpenMP is becoming standard practice. We did a study on Archer, the predecessor ARCHER2, and 30% of the compute CPU hours were 30% of the CPU hours were consumed by programs which had the MPI+OpenMP capability. Whether people were using it, I don't know, but 30% of the cycles were utilized by programs, applications that had this possibility. A few years ago, many people were seeing it as the key to exascale, saying the only way to get to exascale is to have to reduce message overheads by overlapping and doing it at a very high scale with multi-threading. But this may require an MPI thread multiple, and that may then adversely impact performance. Achieving correctness can be hard. You have to consider race conditions, even on maybe your message buffers. Achieving performance is hard because you have to thread the entire application and efficiently. And again, even having written a code which works, you then have to optimize your processes and your threads in terms of the division between processes and threads and all the placement of them. So, think carefully before embarking on this solution. Why do you expect it to go faster? Okay, remember Amdahl's law. Just because the kernel goes faster doesn't mean your whole code will, because if you don't thread your entire code, then it becomes serial in terms of the OpenMP sections. You can the code design may make this easier. If you wrote a code from scratch to be hybrid MPI OpenMP, you could actually, for example, write it in a tasking model. So you basically say, I loop over tasks and execute tasks, And whether those tasks are executed by a thread or a process is rather irrelevant. However, if you're retrofitting OpenMP at a loop-by-loop level, this incremental parallelism may be challenging because it may be challenging to apply that globally to the whole code. As I said, even getting a good hybrid MPI+MP solution, there's quite a lot of messy experimentation. I say system-specific flags and settings. This is making sure that the threads and the processes are scheduled correctly, which is done differently on different systems. So the example I used with XD High and Slurm worked on ARCHER2, but wouldn't be guaranteed to work on another system. So that's a sort of a buyer beware talk. That is the end of that lecture. I'm slightly ahead. So I would maybe do so my plan, because I'm slightly ahead, I might plan to actually just have a half-hour practical session, then lunch and restart at 1:30. Give me a second. Good people, and that's supposed to be I. I don't know if people are maybe people aren't interested, but okay, yeah, fine. Yeah, I think I mean, unless anyone objects, I think that's the right thing to do, because yeah, I think that's fine. I'm slightly ahead of schedule, which is interesting. So I will, as I said, I do need to take a break, but I will share sorry, my laptop is having a bad day. So yeah, so I mean, I think that's probably the best thing to do. So I said the exercise sheet. Just briefly. I'm just trying to share something briefly. So you should see the traffic modeling. So the MPI exercises are just there for interest, and the OpenMP are just there for interest behind it. So yeah, so here I'm really just talking about I really am just talking about performance of the master only model. However, it does illustrate the issues that you might think that you might want to only parallelize the computation and update road, but you have to do the copy back step. Sorry, but it makes a huge difference if you do the copy back step. If you don't parallelize the copy back step, this is just the new equals old, old equals new step. So in fact, maybe also quite interesting to look at the performance if you do or don't parallelize that what looks like a fairly innocuous and trivial copy loop. The second point is just to warn you, code requires that the number of that the road size is exactly an exact multiple number of processes. It doesn't check this just for simplicity. So if you do, you may get a different answer if you so that's why I say set the length of the road to include a factor of 128. That means it will divide exactly on any number of any power of 2 number of processes anyway. The code is deliberately very simple, so it doesn't actually check that. So again, I will stop sharing that now. And again, the last lecture will be at 1:30 when I'll talk about the alternative way, which I think is cleaner, more elegant, maybe not quite so simple, is to actually exploit access to shared memory using MPI's RMA model, as opposed to calling out to an alternative model such as OpenMP. Okay, so this is the final lecture in the course. So I was going to start off by re-showing a slide from the previous talk, which shows you what one of the fundamental problems with hybrid MPI plus OpenMP is. What we want to do is we want to be able to take advantage of the fact that MPI processes, sorry, that the CPU cores on the same shared memory node can in principle share memory directly. And the way we do that in hybrid MPI plus OpenMP is, rather than running one MPI process on each CPU core, we run a smaller number of MPI processes, maybe even one per node, and we eat up the parallelism by using OpenMP. And these OpenMP loops allow us to have shared arrays. The problem with that is that anywhere where you're not using OpenMP, you're wasting resources. And so what would be nice is if we could have MPI processes behaving like threads. And that is what this talk is about. So the MPI shared memory model is MPI processes behaving as threads. So there's a motivation. It's actually quite a short talk, actually, but there's quite a lot of things to digest. There's motivation, there's node local communicators, shared window allocations, and synchronization. But I'll talk about the motivation here. So in OpenMP parallel regions, all threads access shared arrays. Why can't we do this with MPI processes, as we've seen that diagram before? And this is my concern about the MPI plus OpenMP approach, is that you have if you have a serial code, then there is a question to be asked as to whether you should parallelize it or MPI or OpenMP. OpenMP is easier to parallelize, much easier, but it won't scale beyond the node, so you might want to do MPI. So I'm not making any critical statement about OpenMP here. However, when you're doing a hybrid MPI and OpenMP code, you already have an MPI code, almost invariably. So you have some pure MPI performance, and the first thing you do is you basically run it. By serial code, I mean the non-OpenMP code. You run it on a reduced number of processes, because as I said, you have to undersubscribe here. So initially, your code, before you put any OpenMP in, and you say, well, I'm going to run it on one process, not 6, and you lose a factor of perhaps up to a factor of up to 6 in performance. Then, of course, you start adding in OpenMP directives to your loops, and you regain with developer time, the performance, the node performance, and this is serial on a node, the node performance increases with time. But you don't know if you're ever going to get back here again. So that is a problem. So the MPI plus OpenMP is not a kind of a plug and play approach. You can't have a one version which doesn't use OpenMP and one which doesn't, and decide. It's really quite a long undertaking. Now, as I've mentioned before, some people have reported success. Often I said due to kind of threshold effects. For example, I saw a paper where someone said we got a factor of 2 from MPI plus OpenMP compared to MPI, but all it meant was they'd saved enough. Previously, their code was so memory hungry, they could only run, say on ARCHER2, they could only run 64 MPI processes per node, not 128. So by using OpenMP, so that it was a freebie. OpenMP was using up resources which were otherwise unused. If they had more memory, they wouldn't need to do that. Or the threat, so this kind of a threshold effect, or the fixed scalability limit. And I mentioned slab-based FFTs in the previous talk. So there have been people reported successes, very good success for MPI plus OpenMP, but they're often for, as I said, threshold effects. They allow them to go past what is currently a very hard threshold, either in memory or in scalability for parallelization. There are other use cases. Saving memory, as I said, large static lookup tables are possible. MPI, we need 1 copy per process. On ARCHER2, that would be 128 on each node. There is a slight corner case here to do with NUMA-friendly memory allocation, but this was just a hobby of mine. It's very, very rare that you get because because in MPI processes always allocate their own memory. It's very, very unusual for that memory to end up in a different NUMA region from where the process is running. The only time that can happen is if a process uses up all the memory, its local memory, and therefore spills over onto other NUMA regions. That can happen if you have a perhaps temporary, very high memory requirement for rank 0, for example, during the I/O phase. So I have used this shared memory RMA case to solve that, but that's really a bit of a corner case. So what we're going, we haven't covered put and get, and we don't need to, but there is a way of doing remote read and write between processes in MPI, but it requires a function call. And the way it works is ultimately you call function calls MPI get and MPI put, and they're like, an MPI get is like a read without a send, and MPI put is like a send without a receive. And what you say is, I would like to read a certain piece of memory from that process, please, which is an MPI get. Or you say, I would like to write some data into the memory of that process. That's an MPI put. Now, the reason that that's not particularly efficient potentially is you're having to do a function call, an MPI get and MPI put for each data transfer, as opposed to reading and writing directly. However, this does work between nodes. Okay? So standard RMA, the way it works, standard remote memory access, which in MPI put and get model does work between nodes. It works everywhere. There's a stage where processes publish their local memory in a collective window. So for safety, you say as a process, I am going to let other processes access this area of memory. You then publish that, and it's called the window. And then you can do puts and gets to windows. So the window becomes an area of shared memory which you can read and write to using get and put. However, because get and put are single-sided, there's not a send-receive matchup. You need appropriate synchronization, and the appropriate synchronization you do, the easiest one, something called MPI wind fence. It's basically a barrier. So what you do in this model is you allocate a window. You can all do remote reads and write, and then you do a wind fence, which is like a barrier to say, like, we've all finished. So you can do that, but that seems wasteful on a node. If we did that on a node, we would be allocating a shared, collective shared window, a shared area of memory, like a shared array on a node, but accessing it using puts and gets, function calls, which seems crazy. Why can't all processes just read and write directly as in OpenMP? And there is a technically this requires something called the unified model, which I won't go into. But in fact, there is this really just a technicality. But in fact, all standard CPU architectures will allow this. All standard CPU architectures, modern ones, will in principle allow you to processes to read and write directly to a piece of shared memory, not having to use function calls like put or get. The caveat to that is, of course, that read or write requires the processes, the MPI ranks, to be on the same node. So for the first time, we're going to have to talk about nodes. We're going to need a way of identifying all the processes which live on the same node. So what we do is the processes join separate communicators for each node. So we create a subcommunicator, and there is a functionality for doing this, where I always call it com node. You all join a communicator, which would be of size 1 to 8 on ARCHER2, where all the processes in the same node are in the same communicator. You then have a special routine to do shared array allocation across all processes on the node. The way it works is that each process receives a local array. So what you say is, each process says, I'd like to allocate an array of 1,000 integers, for example. If you have 128 processes, in total, you get an array which contains 128,000 integers. However, the clever thing is that this is arranged to be a part of a single global array. So what happens if each process says, I would like 1,000 integers, MPI will allocate an array of 128,000 integers on ARCHER2, and each process will get a subsection of that array. So each process gets a subsection of a large contiguous array. And that means you can do something which is rather nasty, but works. You can access outside the limits of your local array. So local array of -1, instead of being an invalid entry, is the last entry on the previous process. Local array of n is the first entry on the next process. So it sounds like a rather nasty thing to do, but this is what you do. You do a shared array allocation. You get given a small array, but it is actually the operating system is arranged for that to be a subsection of a larger global array. And then you can basically, if you want to read someone else's data, you basically just over-index or under-index your current array. We need appropriate synchronization, because if you're directly reading and writing, you need to think, well, I want to write to this array, but is everybody ready for it to be written to? Or if you want to read data, you say, well, is everyone ready to have the data read? That wouldn't happen with send or receive. If you wanted to receive data from a process with a receive, you would issue a receive, and the data would only be sent to you when the sender was ready. Here you're reading the data directly, so there's a danger you read the data before it's ready. So you need appropriate synchronization, and by far the simplest thing to do is this wind fence. It's basically a barrier across the window, which makes sure that no one enters this section of code before everyone has finished the previous start. Just like MPI plus OpenMP, we still need MPI calls for internode communication. So here you will have, internode communication being done by sends and receives, but intranode communication being done by this slightly weird over or under indexing of arrays. Isn't this what's UB? Sorry. No. So it's only undefined. So it would normally be undefined behavior, yes. Because normally, if you asked for 1,000, an array of size 1,000, yeah, it would, well, what it will do is, let's think, are you a C programmer or a Fortran programmer? Sorry, are you a C programmer? Just are you C or Fortran? Just I'm going to do a little example. Okay, see. So if you're a C programmer, what can happen? Imagine you've just got two processes on a node, okay, and you want to have what you could have is you could do the operating system could do the operating system could do a single malloc, big array equals int star malloc. I'm going to get the syntax wrong of 2,000 times size of int. Yeah. So I've got my that int star didn't really. So that's supposed to be. Yeah, that's. Let me actually do. Let's share a different window. This is not going to work in this. So can you see? Yeah. So you're doing something like int star global array star local array. Yeah. And the global array equals int star malloc of 2000 times size of int. Okay. On rank 0, local array equals global array. This is sort of pseudocode. So here, you know, so here, local array of -5 is perfectly well defined, even in normal C, because you know you've allowed the space. It's just pointer. You're going back the way, and local array of 1002. Does that make sense? That's sort of what it's doing. So remember, arrays are just pointers in C. So does that make sense? That's sort of what it's doing. Yeah, it's basically doing a big allocate in shared memory, which requires special operating system kind of. Yeah. Yes, so they're not allocated. So I said they were allocated locally and put together. They're not. Sorry. So when I said allocated locally, what I meant was if you ask for an array of size 1,000, you get an array of size 1,000. However, they are actually subarrays of a larger array. So yeah, they're not allocated separately. It's allocated as a large global array and then divvied up and sectioned up. Sorry. Does that make sense? Yeah. Okay. So and you have to do special operation system trickery to do that using things like shared memory segments, because normally you get a segmentation fault if you so this is done as I think using Unix shared memory segments, if I remember correctly, but I'm not an operation system person. If we look at yes, that's right. So the first thing is how do we produce a communicator for each node? Well, what people used to do is they used to do this get processor name. So all the processes on the same node would get the same string, node 53 or node 54, and then you would get together and everyone with the same string for their get processor name would join the same communicator. That's really a bit of a hassle. So they've created this generic routine called MPI split type. What this says is you can split the communicator down based on a split type. And the split type, the idea is the split type could be something like level 3 cache. You could say, let's split the communicator into subgroups where each subgroup shares the same level 3 cache. But the last time I looked, the only supported splits type was MPI type shared. So there may be no now. It was originally introduced to allow you to create subcommunicators where all the processes live on the same node, the same shared memory node, MPI-COM, so they share memory. However, it's not a specific routine for that. It's a generic routine which takes a split type. And that, for example, you might want to communicate to where of all the processes that have GPUs on them and all the processes that don't have GPUs, for example. So it's there for future extension. So you give it an input communicator. You specify the split type, which here is always going to be MPI-COM type shared. You specify a key. The key is the tiebreaker. So the key, well, the key defines the ordering of the ranks in the subcommunicator. So I always pass my rank there. There's some info which I've never used. It's basically a hint thing, and you get back a new com. So the key controls the rank ordering within the subcommunicator. I just use MPI info null. There will be, I don't know what those options are. I have to say, sorry, I don't know what options. You'd have to look at the man page to see what options are valid, but I've never used them. I just do MPI split, MPI-COM split type, MPI-COM world, MPI-COM type shared. I pass my global rank as the key so that the ordering in the subcommunicator is the same as the ordering in COM world, and I get back a new communicator, always called node COM. So for example, here I do MPI-COM split type, MPI-COM world, MPI-COM type shared, rank. So this means they're ordered by their original rank, MPI info null node COM. So if I started off with a COM world of size equals 12, so I have a machine with two nodes, two shared memory nodes, each with six CPU cores. So my original COM world has size equals 12, and my rank is 0 to 11. If I then call MPI-COM split type on node COM, each of these belongs to its own node COM, where node COM is of size 6, and the ranks are always, remember your rank is always between 0 and the size of the communicator minus 1. So these guys happen to have the same rank in node COM as they do in COM world. These guys don't. These guys have 0, 1, 2, 3, 4, 5. So that's the way you do it. And it's actually quite a nice, so for example, somebody mentioned I/O before. They asked how many processes on each node should do I/O. I said it should be, not all of them, but maybe one or maybe a couple. You might have asked at that point, well, how do I identify all the processes that are on the same node? Well, you could do MPI-COM split type, and you would then get a subcommunicator, and you could say, within that subcommunicator, which will be of size on ARCHER2 128, you could pick some subset of those ranks to do the I/O. So MPI-COM split type is actually quite a useful routine in general. Then, sorry, my mouse is playing up. I have a new mouse. Then to allocate the array, it's called MPI win allocate shared. So what you're saying is, I want to get a shared window. It's a bit like a malloc, but there's a number of caveats. First of all, it's called by all the processes in this communicator. It's collective across the communicator, but of course the communicator has to be one where all the processes are in the same node. If you passed in MPI-COM worlds here and COM world was on multiple nodes, it would complain. So basically, this is just like a malloc, where you get back a base pointer, which is the pointer to the pointer to your part of the subarray. Okay? But there are lots of stuff in here. You pass the size, which is the number of bytes you want, just like a malloc. You pass a hints object called info, which I've never used. I just use MPI info null. You also pass a displacement unit. We're not going to use that here. If you were to use MPI put and get, then the displacement unit is significant. It's the counting unit. So when you do MPI put and get, you say, I would like to write this data into location 7 of my neighbor's window. What does 7 mean? Is it 7 integers, 7 doubles? Well, that's the displacement unit. You would do that size of integer, size of double. It gives you a common, convenient counting base, but we're not going to use that here. We're not going to use put and get, so that's irrelevant here. I mean, you might as well pass it, but it's not actually useful here. And as I said, you get back pointer to your local array. Again, this window is useful because this window refers to all of them. So if you want to do synchronization, you do synchronization on the window. So it's slightly weird, but you get back two things. You get a pointer to your local data, which is a sub portion of a large piece of data, and you get an object called a window, which identifies all the processes basically. So when you want to do synchronization, you do synchronization on the window. That's of type MPI win. So the size is the window size in bytes. The displacement unit is the counting unit, which you're not going to need. The COM is the parent COM, must be with a single node. The base point is allocated storage, and the window is the allocated is what MPI calls an allocated window. Gives you the window. So the traffic model example is basically, if you look at the code, it might be worth me looking at the code here. What we're having to do is this update road requires access to your local cell I, but I+1 and I-1. And so because of that, you have issues at the boundaries. So before we do that update, we do this halo swap where we exchange our boundary cells with our neighbor. So we send we send off, we set our old road of 0 to be our neighbor's extreme value, and our old road of n local. So this is the halo swapping bit. Okay. So because you cannot read and write directly to the other process's memory, you have to do this halo swapping. So have I actually? So I have not shared that again. So apologies. I have when I try and share a terminal, it doesn't work the first time. Apologies about that. So just to reiterate, yeah, fine. Yeah, it for some reason switch to a terminal is so. This update requires access to old road, to old road of I+1 and I-1, and that means that the boundaries of your domain, you need data from another process. So prior to doing this update in the parallel code, you need to do this halo swap where you exchange your boundary data. You place so you send your extreme data, which is your leftmost value, becomes goes to the rightmost halo of your neighbor, and the same for the other. So this is halo swapping. How can we do that? Do we need to do that with shared memory? We don't need to do that. We could read and write that data directly by doing this over-indexing, under-indexing trick. So I'll show you how that works. So in the traffic model example, we do MPI com node com, int old road, MPI win node win size and displacement unit. So the win size is basically we want to have an array of size n local plus 2. Now we're still putting this slightly confusing, but I'm assuming here that all the local arrays still have halos. That's because the guys at the end will still need to do send receive. So what I'm doing here is I've got halos and I'm just filling them in by doing direct copy rather than message passing. You might actually just choose to just read to actually access the data. But the model I've got here is we've still got halos, we've still got local copies of the off process data, but rather than doing send and receive, we're directly reading into it. So I still have a halo here. I display, so MPI win I create shared win size, which is n local plus 2 times size of int, displacement unit and integers, info null, Node com is something I previously computed. I now get the old road back as a pointer, so it's now pointing to this data, this allocated data, and node win is my window, MPI win, node win. I need this for doing synchronization. I need this for doing direct read and write. And the way I can do it is if I have an array called X, node rank. So if n local is 2, then the arrays of size 4 are 0, 1, 2, and 3. So I've only got 2 cells locally. What I want to do is I want to write data into. So let's think I now have a choice. When I do the halo swapping, I can either write my data into my neighbors or read my data from it. But the point is that here, x of 0 is that value, x of 1 is that value on your neighbor, x of 3 is that value, x of 4 is that value, x7 is that value. That x7 is this guy's x3. So these pointers have just been messed about with. So the default is a contiguous block of memory across process. You can actually relax that and have non-contiguous. I don't really see why that would be useful, I have to say. You can tell MPI you don't need it to be contiguous across processes, but I don't see how that would be useful, at least the applications which I've seen. So that's how it works, and it does look a bit ugly, but it's all semi-legitimate. So the only thing is here, in the previous diagram, rank 1 can access rank 0's x0 by referring to its own x minus 4. So imagine I wanted to basically access that value. It could be x minus 1, minus 2, minus 3, minus 4. Okay. It might be more convenient to reference as x, have an array. It might be nice for me to actually say, well, I would actually just like to know what the pointer is here. If I knew what this pointer here was, call it x0, I could reference it as x0 of 0. And you could say, well, how do I find out address x0? Well, rank 0 could just send me its value. Could rank 0 just MPI send me its pointer? Now, you can't do that because of the way that shared virtual memory works. Separate processes can have different virtual addresses for the same physical location. In other words, the pointer value that node rank of 0 uses to reference that would not be valid on node rank 1. This is a slight technicality, but if you want to find out what the address of an object is on a different process, you have to use a slightly bizarre routine called MPI win shared query. It's something of a technicality, but this happens when, not in this situation, but when, for example, you decide to have you want to have a lookup table, and you might decide to just allocate that lookup table on rank 0. So if you did that, when you did the MPI alloc win alloc shared, rank 0 would specify a large value of win size, and all the other guys would specify nothing. So all the data would then be allocated on rank 0. The question then is, how do you find out what the pointer on rank 0 is, to reference that data? You cannot just send those pointers round and send and receive, because they're no longer valid in different because of the way that virtual memory works. So you have to do this MPI win shared query. It's a bit of a technicality, but I just mentioned it here. So halo swapping, that becomes now we can do halo swapping by direct copies. We need to ensure the data is ready beforehand and available afterwards. In other words, I'm going to do halo swapping I'm doing it by writing. I'm going to write into the halo of the guy up, old road of n local plus 2 is old road of n local. That is saying n local. Yeah, it writes that. So yeah, n local plus, yeah. That's doing the halo update by writing. And old road of -1 is old road of 1. However, you can't just do these in isolation. You have to call an MPI win fence to make sure that here that you're allowed to write to old road on the neighboring process, that he or she's finished with it, and here you want to say, right, I've finished doing everything. So MPI win fence The zero there there are a bunch of hints you can specify, but I always just specify zero. So this is basically a barrier in time and a memory flush. So basically, whenever you do, the simplest way of doing this is whenever you do, it's equivalent to a barrier in OpenMP. It has exactly the same effects as a barrier in OpenMP. Make sure that everybody is ready to do the shared memory operation. So you would encompass similar statements in OpenMP with barriers. In an MPI, you encompass with MPI wind fences. So yeah. So the MPI wind fence takes hints, but I just use the default of 0. So the off-node comms, the direct read and write only works within a node. You still need MPI calls for internode. So you need to nominate a couple of, well, you could not, I mean, here, because every rank has access to all the data, any rank could do the send and receive, but the natural thing is for rank 0 to send off its boundary data left to right, and the highest rank 127 on ARCHER2 to send its data up the way. You could actually do any rank. And this send receive has to take place in COM world, because you're explicitly referencing processes which are not in node COM. So you have local operations, shared memory operations with fences on node COM, but your original send and receives take place in COM world. So it's a bit of a run through, but I mean, it's relatively, it's a relatively simple syntax for shared memory and MPI. It's much better than rolling your own. You can try and roll your own solutions using system calls to things like POSIX, shared memory segments and things, but you should not do that. This is a much better way of doing it. The possible use cases are on-node communications without needing MPI, or one copy of a static data per node, not per process. The advantages is an incremental plug-and-play approach, unlike MPI plus OpenMP. In other words, you can have a version of a routine which uses MPI send-receive or MPI shared memory, and you can just swap them in and out, see which one is faster. Excuse me. The disadvantage is you don't have any of the technology of OpenMP for doing OMP parallel 4 and splitting up the loops and such like. And also, depending on how you write your code, the global array may have halo data sprinkled inside. So it's a bit ugly the way I've done this. By leaving the halos on all the local arrays, my global array is, so I'm trying to get the pointer up here. Is it control? Yeah, it has garbage data, real data, real data, garbage data, garbage data, real data, real data, garbage data. So there are some practical implementation concerns, but I like it because it allows you to decide routine by routine. Am I going to treat the processes here like processes with send and receive, or am I going to treat them like threads where they can do direct read and write? And at runtime, when you go onto a new platform, you can just run the two versions and you can see which one is fastest. The conclusion, okay, possible use advantages, plug and play approach. But there's no, as I said, these are the disadvantages. So I think just finally, I will just show you, I mean, end of a long couple of days and it's a Friday, I will just show you the solution and very briefly talk you through it. So I want to share this one. So if you look here, there are a bunch of solutions. The C hybrid is basically, it's really very simple. This is the hybrid MPI OpenMP, but it's basically I don't provide you a solution. Apologies. I don't provide a solution. I just provide an Archer job. Apologies. I forgot that. I want to go to C. So I haven't downloaded the solutions. They're on the web. Okay, CDC MPI. see MPI RMA. So it's the traffic shared memory is the solution, and you'll see that it basically is very like the MPI version, except we have a few node variables, node size, node rank, and such like. I'm going to use MPI max process. I'm going to use the MPI get processor name to print out some diagnostics, so you'll see how to use it. So create node local communicator. This is MPI conf split type. We've seen that already. Yeah, this is where I, just to check, I get my node name and I get the size and rank. So I say, you know, rank blind com world is rank blind node com and on node blah. This is, I just print out all the debugging just to make sure that things worked as I expected. In the original code, you malloc old road, but we're not going to malloc old. Old road is the one where you need to use the I+1, I-1 indexing. So we do the code we've already seen. The MPI when allocate shared. Then all this code is just the same as it was before, except, yeah, here. Instead of send receive as we had in the other code, I do a win fence. I am writing the Halo data here to my neighbor. I'm writing the Halo data down the way, and then I fence. So that section code there on node does the Halo swapping. However, I still need to do the off node Halo swapping. So I say, if I'm on the very right hand side of the process of the share, if node rank is node size -1, I do a send and a receive. Else, if node rank equals 0, I'm right down the end, I do a receive and a send. That was just a, so that's basically it. This is the internode stuff, and this is the intranode stuff done by this what looks like nasty over and under indexing trick. And if you compile and run this, you'll see it does actually work. If you're interested in the other use case, which is a shared so someone asked this on, so if I share the sorry. If I oops, sorry, I'm right, this is what I wanted. Can you see that? This working? Yes. So if you do MPI shared memory stack overflow, and maybe do my name Henty. Yeah, can I use MPI? And I posted here an example, which basically, how long ago was this? A long time ago. Which basically does this trick where it allocates a lookup table on only one process node rank 0 actually allocates an initial table onto us, so node can read it. So basically, I allocate a. So basically, I say the local table size is 0, else if I'm not ranked 0 on a node. So here in this MPI when allocate shared, actually all the data is being allocated by rank 0. And we need to do this trick. We need to get a local point of value out. If node rank is not 0, we need to do this MPI win shared query. We need to say, yeah, it's slightly complicated syntax, but this is basically getting me a pointer from this process, which actually is valid to reference the data on another process. So you need to call MPI win shared query. Need to get local point of validity. It's a slight technicality, but it's a bit nasty. You could do the over/under indexing trick here, but it's maybe not so elegant. So really, that's all I had to say. Thanks for staying around. I'll be around for 10 or 15 minutes if you have any questions. Well, I'm available by email if you have any general questions. If there's anything that's come up you want to follow up, then you can either email me or send in something to the ARCHER2 help desk. That's always open. I'm really interested in people's people's issues with MPI, or even if it's stuff we've not covered here. I'm very interested in helping people, trying to understand what people do with MPI in real applications, and give you some advice. I hope you find it useful. Apologies, it was a bit of a rush through at times, but it's a bit difficult with an advanced course to know whether to go relatively rapidly so you cover a lot of ground, or to go slowly, but then people who aren't interested in the topic are not interested for a long time. But I hope the example programs will provide a framework, at least illustrating you how to use these things in practice. So thanks a lot for your attention, and have a good weekend. I don't know if anyone's going to be supporting England at the weekend. Good luck if you are. Football, I think you're going to need the luck.
Great, thanks. It's been really interesting.
Yeah, that's good. And you had a chance to try that UCX trick. Maybe you haven't had a chance yet.
Yes, I get about a 5% increase. So a 5% reduction in the total time of the total program. I haven't had a chance to kind of dig into the profile yet.
I mean, it's very data dependent, so it tends to help a lot for massive all-to-alls on large. How many processors are you running on? What scale?
So for that one, it's 8,192.
Okay, so you are running at scale. Okay, fine.
Yeah, but I'm also underfilling, so I'm either only doing 64 or sometimes only 32 cores per node. So there's a lot. There's, I think, either 128 or 256.
Okay, so no, so you're not being hit by this problem then, because they may have fixed it eventually in OFI, but when it was a bad problem, it would have been an order of magnitude. In fact, your previous code would have just not run. Your previous code would have basically, well, fallen over in a heap. So I thought it would still have a benefit, but okay, so it doesn't sound particularly. It's marginal. The problem is that UCX has slower point-to-point performance, so it swings and roundabouts. But no, okay, so it might be worth using, but it's not the dramatic thing. Some density functional codes like VASP and things which do huge numbers of plain wave codes that lots of FFTs really struggle with OFI. You have to do the UCX stuff. Anyway, okay, that was just a suggestion.
Yeah, just out of interest, what did UCX do differently to OFI for the collectives that makes it this different behavior?
I don't think the collectives are different. I think it's just that, at the very low level, MPI is saying, could you please send a megabyte of data from this process to that process? And there is some protocol for getting that onto the network. And the Cray, HPE used the OFI Open Fabrics interface as a portable way of doing that, interfacing between the application and the hardware. But it seems to have problems. For slightly bizarre reasons, although we have a Cray Slingshot interconnect on ARCHER2, we got a very early machine, so the network cards, the cards that interface between the processor and the network, are not HPE. They were meant to be. They're not. They're Mellanox, and Mellanox has its own protocol called UCX. So it's a bit of a quirk that we can. They just do different stuff. It's really it's just using a different protocol for interfacing between the hardware and the network. So it's well below the level of MPI. MPI, it's way down below what MPI is still just saying, could you send this many bytes from here to here, please? It's just being done in a different way. Does that make sense? And yes. It just seems that OFI clams up. If you really hammer OFI with data, with large collections, it just seems to suffer from congestion. It suffers from congestion in a way that UCX doesn't. Of course, UCX was written for these cards because they're Mellanox cards, and the OFI is a portable thing, so maybe that's why. But it's really
okay,
I'm trying to think of
slightly better scheduling for that.
But it's very low level, yeah.
Okay, I see. No, that's
okay.
good to know.
Maybe that didn't work. Okay, take care.
All right, thank you very much. Have a good weekend.